So, we have written the first law of thermodynamics, which states that the rate of change of internal energy of the system per unit mass, the change of internal energy per unit mass of the system is sum total of the heat added to the system plus work done on the system. Now, the internal energy, as already mentioned, is a state variable that it depends only on the initial and final state of the system, irrespective of the process or path through which this change is taking place. However, this amount of heat added and amount of work done, they are measure of external effects, and each of them depend on the path or in which the transition has taken place, that is changes from one state to other state. However, it is the law states that these two path dependent variables, sum of these path dependent variables is independent of the path. This is the first law of thermodynamics as stated in classical thermodynamics, and refers to a system which is in equilibrium, that is, if we consider the system to be certain mass of gas, that is when the gas is at rest. So, of course, if we want to apply this for a flowing fluid or a moving fluid, then the energy content is not only the internal energy, but also say the kinetic energy and maybe other change in other form of energy like potential energy and all are possible. So, this energy will then contain the kinetic energy and if necessary potential energy as well. Now, as you said that Q and W are path dependent variables, E is state variable, Q and W are called path dependent variables or path variables. Now, if somehow that the system is thermally isolated from its surrounding, that is when the system is thermally isolated from the surrounding, no heat exchange can occur, and if then any change takes place, then the change will be due to the work done only, and any change in state in such a situation in this condition is called adiabatic. That is any changes in the system which takes place without heat transfer, then the change is called adiabatic. Similarly, if there are various other changes like isothermal, where no change in temperature takes place, the process or the change may be isobaric, that is the pressure is remaining constant while other changes in other variables are allowed, and so on. Now, looking to the work, see, the most important way of performing work on the system is by compression. So, most important approach of performing work is compression, and if the compression is allowed in such a way that the system passes a succession of equilibrium states, then this work done by compression can be expressed analytically. So, let us look to that. So, most important way of performing work that is compression or expansion. And analytic expression for this work is possible if the changes are made in such a way that the system passes through a succession of equilibrium states, that is the system always in some equilibrium state, and that type of changes are called reversible. So, reversible changes that is system passes through succession of equilibrium states. Now, this is possible if the changes are very, very slow, if the changes are extremely slow, possible only if the changes extremely slow. And in this case, the direction of change has no effect. The direction of change has no effect. Now, if we consider then say a compressive work, then that extremely slow compressive work, then at each stage, during each stage of change, that is during an infinitesimal amount of change, the pressure practically remains uniform and the work is due to a small decrease in volume. So, the compressive work then work by compression, of course, reversible compression is P delta V, and since the volume is decreasing, so this is P delta V. So, hence for infinitesimal reversible transition from one state to other, hence for infinitesimal reversible change, from one state to another, the first law of thermodynamics now becomes delta E equal to delta Q minus P delta V, or of course, we can write in differential form. Now, again see this particular path by which initial and final state are joined is relevant. For a finite change, the path is relevant. Since P is usually not a function of V alone. So, this is the first law of thermodynamics in differential form or infinitesimal form, and in classical thermodynamics applied to a fluid at rest. For moving fluid, this internal energy must contain the other form of energy also. So, you can write that for moving fluid, other forms of energy, say kinetic, should be added to E, and the equation is then the energy equation for flow. So, the basic energy equation or basic form of the energy equation for a moving fluid is the same, where E now represented as the internal energy plus kinetic energy. With this, now we will try to define a very important practical quantity known as the specific heat. Of course, amount of heat required to rise a temperature, unit rise in temperature in a small reversible change. So, amount of heat required for unit rise in temperature in unit mass of the system in an or say in a small reversible change. So, if we define the specific heat by C, then C becomes delta Q by delta T. Now, of course, see this is not uniquely this is of course not uniquely defined, because we have not specified how this change has taken place. Not uniquely defined. Since the conditions under which the changes occur are not specified. See, this we can explain this way, that a state of the system is just a point in the indicator diagram, say P V. Indicator diagram, and a point represents a state, because in the indicator diagram a point fixes pressure and specific volume, and as we have mentioned earlier that for a pure substance, if we fix any two variable, then all other remaining state variables are fixed automatically. Consequently, a state represents a point. State is represented by a point. Now, the change of this state can occur in an infinite number of ways. Change can occur in infinite number of ways. That is, this is the current state of a certain system, and let us say we change it infinitesimally. This change can occur along this direction, or along this direction, or along this direction, along this direction, or any such direction. So, these are all direction of change, and since there are infinite number of neighborhood points of this particular point, so we have infinite number of ways of this change. So, if we a small reversible change, which can be denoted by say delta p delta v, can proceed in any direction. Now, assuming that the only work is done by compression, say assuming only work done by compression, we have delta q is d E d p at constant volume into delta p plus d E d v at constant pressure into delta v. That is, we have written E as a function of pressure and volume plus P delta v, and similarly the change in temperature is also a function of pressure and volume, can be written as dT dP at constant volume into delta P plus so, this shows that C equal to delta q delta T depends on delta P by delta V. That is on the path. Direction of change. Now, if we consider say two very important, so two particular choice or two particular important choice, two particular important choice one is change at constant pressure, change at constant pressure, and the other is change at constant volume, constant specific volume of course, constant specific volume, and these two gives two principal specific heats. Cp, that specific heat at constant pressure, and specific heat at constant volume. Specific heat at constant pressure and specific heat at constant volume that is Cp is dT at constant pressure, which from the earlier equation can be written as dE dt at constant pressure plus P dV dt at constant pressure, and Cv is dQ dt at constant volume, which is simply dE dt at constant volume. The ratio of the two specific heats is a very important parameter in fluid dynamics. Cp by Cv, which can be shown to be dP dV adiabatic dP dV isothermal with the specific heats. We will define a very important fluid dynamic parameter, which is say known as the bulk modulus. So, bulk modulus of elasticity which you know the volumetric stress by volumetric strain, and so now the volumetric stress is delta P and the volumetric strain is, so the delta V by V, and we know that if it is a compression then the volume will decrease. So, it is actually when pressure increases volume decreases. So, it will have a negative sign, or we can write this to be minus V dP dV. Now, of course, in fluid dynamics the inverse of this parameter is more important. is and which is called coefficient of compressibility. So, the coefficient of compressibility is defined as and since the inverse of the specific volume is density, this becomes to be 1 by rho 1 by rho d rho by dp, 1 by rho d rho by dp, rho equal to 1 by v is density, and is a more preferred variable than specific volume in fluid dynamics. Now, since these definitions also involves dp dv, hence they are also path dependent. So, bulk modulus or coefficient of compressibility are also path dependent. So, bulk modulus and coefficient of compressibility depends on the path that the change follows. That is, on each path the values will have be different, and again, so two particular changes, two particular significant definitions are isothermal and adiabatic bulk modulus. So, here also we will have isothermal and adiabatic bulk modulus, and from first again that their ratio will be equal to the ratio of principal specific heats. that is ratio of the two corresponding bulk modulus, that is adiabatic bulk modulus by isothermal bulk modulus is again Cp by Cv. Now, each pure substance is represented by a simple equation of state, as you have already mentioned that for a pure substance any state variable can be expressed by two other state variables, and this equation is known as the equation of state. So, for a pure substance we have one simple specific heat, one simple equation of state involving 3 parameters, 3 state variables. The most important equation of state or the thermal equation of state is called the perfect gas law, or where P is given by rho or T. Pure substance, of course, we are concerned only with gases. So, it is gas. So, thermal equation of state is or say P is a function of specific volume and T, or for fluid dynamics, as we said that density is a more preferred variable than specific volume. This the most important widely used is equation of state of a perfect gas. Which is P equal to rho R T, where T is in degree Kelvin, T is in degree Kelvin or degree Rankine, and R is specific gas constant, which is universal gas constant by molecular weight. Universal gas constant, and m is molecular weight. Now, this equation holds for all gases at low densities, particularly when the temperature is not very large and neither the pressure is too high. So, now this is the equation of state for a perfect gas. Perfect gas are those gases, of course, these are hypothetical gases which is made up of molecules which are Hertz sphere without having any intermolecular forces, and when they collide they follows perfect collision. Of course, no gases under all conditions follows perfect gas law. However, as we mentioned already that almost all gases, particularly at low densities, are so that P equal to rho r T holds for almost all gases, at low densities. Very low and pressure is not very high. For a pure gas. We have already mentioned that the T must be expressed in absolute scale, T in absolute scale, that is degree K or degree R, and as you know that degree K is degree centigrade plus 273.16 and degree Rankine is degree Fahrenheit plus 459.69. In aerodynamics, the fluid concerned is usually air, and for air this equation of state is a very good approximation unless the temperature is not extremely low or the pressure is not extremely high. Of course, since air is not a pure substance, it is a mixture. So, at very high temperature also, due to the chemical reactions and thermal reactions that may occur, then this equation of state can be modified accordingly for the mixture. However, as I have already mentioned that all gases at low densities approach a perfect gas. Now, the caloric equation for a perfect gas is caloric equation of state of a perfect gas is that E is a function of E varies, E is simply a function of T, or we find that E equal to C V T. Now, let us say a few words how this equation of state will change for a real gas. We know that all real gases liquefy. It is all real gases liquefies, all real gases liquefy, and there is a maximum temperature where this can occur, that is above this temperature under any condition this gas cannot be liquefied. So, that temperature is called T c. Let us say call the critical temperature T c. Critical temperature T c. So, at any temperature above T c, the gas cannot be liquefied that is whatever we pressure we apply, if the temperature is above this temperature the gas cannot be liquefied. So, T c is the highest temperature at which the gas can be liquefied. T c is the highest temperature at which the gas can be liquefied. And the corresponding pressure and density or corresponding pressure and density are, let us denote them as density are P c and rho c. Now, these critical variables are characteristics of a gas. Critical variables are characteristics of a gas, that is they are fixed for a certain gas, like an identity of the gas. Critical variables are characteristics of gas, that is each gas is its own fixed critical temperature and critical pressure and of course, they depends on the intermolecular forces that are present between the molecules of the gas. Now, at critical point at critical point, this is the condition that is satisfied. And an equation of state for a real gas equation of state for a real gas involves two additional characteristic variables, of course besides R. R is a characteristic variable and an equation of state for a real gas will involve two additional characteristic variable, say one of these, two of these three, T c, P c and rho c or V c. And as you know that most widely used real gas equation of state is the van der Waals equation. Of course, there are many such equations. And these two constant alpha and beta are given as alpha by beta is 27 by 8 RTC and alpha by beta square is 27 PC. And the internal energy of a van der Waals gas is given as now we define a very important parameter which is known as the compressibility factor of a gas. Usually denoted by Z is P by rho R T. So, the perfect gas has compressibility factor Z equal to 1. So, you see that it actually also measures the departure from perfect gas behavior. Z equal to 1. So, you can see that Z measures a departure from perfect gas behavior. So, before we proceed further, let us say what we have discussed today. We have discussed the first law of thermodynamics or the statement of energy conservation. We have defined several processes, adiabatic, isothermal and so on. Also, we have discussed what are reversible processes, and we have discussed about the specific heats, different type of specific heats, in particular to principal specific heats, and again to principal bulk modulus and coefficient of compressibility. And finally, we have discussed about equation of state, in particular perfect gas equation of state, and have also discussed briefly how this equation of state should be changed if we consider the real behavior of the gas, particularly at low temperature and high pressure. And with this, we will now move on to a discussion on second law of thermodynamics and try to develop some additional relationship which are particularly useful in high speed aerodynamics. And so our next discussion will be on second law of thermodynamics, but that is in the next lecture.